The first thing I want to do is to thank the organizers for the invitation and also for arranging such a wonderful conference. It has been great talks and, well, great moments here. I was a postdoc here like for 2 years, so it's always nostalgic to be back. Okay, usually I hate long titles, but this is, well, the original title of the paper that I just submitted to the archive yesterday. So all the information will be available there. This is a joint work with Georg Cantor and Miguel Cardona. Well, yeah, talking about this notion of filter-linkedness. It's actually some very natural notion. You will not be impressed when you see it. Okay. So, okay, let's start with some preliminaries. So we have seen a lot of cardinal invariants in here. Some of them. So space for any two functions f and g, well, we have this relation called where we say that f is dominated by g or eventually dominated by g, or this other one saying that f and g are eventually different, meaning that they are pointwise different from some point onwards. Considering the fused relation, we have these two cardinal invariants. Well, very typical, the unbounded number, which is the smallest size of an unbounded family with respect to this relation, and the dual D, which is the smallest size of a cofinal family. And well, I will talk a lot about the almost disjointed number. We have seen a lot of math families in this conference as well. And well, maybe just refer a little bit to Bartoszyński characterizations of the uniformity and the covering of Meagher, which is just like the bounding and dominating number, but with respect to the relation of being eventually different, right? So well, the title says preservation of cardinal invariants, but I will focus mostly on the almost disjointed number. So just like to review some example of preservations of math families, well, I will just review like very classical and just very few ones. Like I know Osvaldo like has a much longer list about preservations of math families. So one of the classical results is that, well, from CH, you can construct a math family that can be preserved by any co-enforcing extension. Somewhat nice version of this theorem due to step-runs is that adding omega-1 many cohen reals gives you a math family that can be preserved by further co-enforcing extensions. A bit in relation with that, but maybe not that directly, is a recent result of Brendle and Fisher, when they proved that for arbitrary regular values, you can always separate A and S, okay, or BA and S in this way. So the main technique is, well, they use a matrix iteration. In the vertical axis, they add a math family, and then through the parallel iterations, they want to preserve that math family. So this is a preservation of a math family. I will talk about the type of math family that is involved here in the theorem, and as well, it's also related to a step-runs result. So this family is constructed by the Hechler's poset for adding a math family. Just to review the definition, so we denote this by Hx for a set S, which will be like the support of the almost disjoint family. So the conditions, well, they just look like this. I look at the plane x times omega, and you look at finite partial functions that are defined on a rectangle like this. Okay, a partial finite function that gives only value. Okay, so the purpose is that at each point of the horizontal axis, you are going to define vertically an infinite subset of omega. So then the order will tell you that what you generated is actually an almost disjoint family. So the order is just extension in the natural way, but additionally, you have that for the old members of the support. Well, yeah, you extend, but with the condition that at every horizontal section restricted to this first support, you have only at most one, only one. You can have only a chain of zeros or a chain with only appears one. Okay? So this tells you that, well, this condition, this blue condition here, will force that from this point onwards, the infinite sets that are generated vertically, they don't intersect. And this will give you an almost disjoint family, okay? Given by the vertical sections. So now this almost disjoint family is maximal when the set is uncountable. Okay, this is like very classical. And well, just to mention some few properties of the forcing, well, it's CCC, even more it has precaliber omega 1. It behaves very well by embeddings, and even more, the quotient is nicely definable. As you can talk about the quotient, you can also translate the set as a finite support iteration. So just this one good property is that it preserves direct limits, meaning that if you have a chain of sets and you take the h of the union, it will be the direct limit of the hx that come from the chain. So in particular, as it behaves like at limit step, you could think as limit, then any h delta can be thought as a finite support iteration of nice sigma center sets. Now, on one hand, when the support is countable, we always have that the set is just coenforcing, of course, because hx will be countable. And as I said, as you can, now if we look at h omega 1, if you look at h omega 1 as a finite support iteration, well, it's a finite support iteration of countable sets, so it will just be c omega, well, adding omega 1 cohen reals, it will be the same. So in relation to preserving the math family added by this Hechler poset, well, in a work from 2 years ago, but that it was published at the beginning of this year, we somewhat generalized Stepan's result in the following way. So for a regular cardinal kappa, after we add the math family using this Hechler forcing at kappa, we can preserve the math family in further finite support iterations when the iterants satisfy either one of these two conditions. First, either when you iterate with cohen forcing, random forcing, or the standard sigma center poset that adds an eventually different real, which we denote by E, or if you add a small posets, or iterate with a small posets, okay? So if you look at kappa omega 1, as h omega 1 is just adding omega 1 cohen reals, well, this somewhat generalized Stepan's result. We could see this as a two-step iteration where you first iterate with h kappa. Oh man. And then you do well the iteration. And this somewhat is reconstructed by doing a matrix iteration when in the vertical you just add your math family and then you can reconstruct everything through parallel iterations. So the main point in this result is that random forcing and E, they are good for preserving math families of this type, okay? But well, but this is like a bit general, but not that general because we are looking just at some like very specific things. So we wonder if this could be generalized, I don't know, in some nice way. So first by myself, I was looking at this and somehow this inspired the definition of Frechet-linkedness. So this is like related to the Frechet filter, the filter of cofinite sets. So we have a poset. This is a property of subsets of a poset. So we say that a subset of a poset is Frechet-linked if whenever you have a countable sequence in the set, you can find some condition in the forcing, not necessarily inside P, sorry, such that it forces that infinitely many of the PNs are in the generic. Okay. So this is just like a property of subsets of P. So later, with examples, I will say much more about this, especially about the motivation. As it's a notion, like a notion of linkedness, you can talk about mu linked, mu Frechet linked, which only means that, well, your forcing is only the union of at most mu many filter linked sets. Or also you have a Nasser definition. Yeah?
There must be something additional in the first definition, right? Because if you just, what if is an anti-chain?
No, well, but it's for Q, right? So Q is filter linked, only Q is a subset, right? So it's like when you say linked, data set is linked, okay, or data set is centered. It's a property of the set, not of the forcing, okay? Yeah, so the first is only a property of subsets of the forcing, but the other two are properties of the forcing. Okay? Okay? So yeah, you also have a Nasser definition defined in a natural way. Your set is kappa, your forcing is kappa filter Nasser if and only if, well, any set of size kappa can be reduced to a linked set of size kappa. So one nice property is that, well, the Nasser property for the Frechet filter implies the natural Nasser property. So this is a consequence of a classical theorem of Horn and Tarski. So just to go inside some examples, when the trivial example is used that, one trivial example is used that every set of size mu is mu Frechet linked. Well, you just take singletons and that's it. This is actually what it's, I think the main motivation for this definition is actually this one, that the forcing adding an eventually different real is sigma Frechet linked. Okay, so why this notion? The reason is that, well, one classical result is that this forcing doesn't add dominating reals. And inside the proof, actually what they use to state that this forcing doesn't have dominating reals is this Frechet linked. So just to talk a little bit about this forcing, so we say that a pair is in the forcing if and only if, well, this is a finite sequence of natural numbers, S is a finite sequence of natural numbers, and we have that for some natural number, phi is a sequence of an infinite sequence of finite subsets of, well, or subsets of omega of size at most m. Okay, you can see the forcing more or less like this. So you have your S, and in other part you have, well, your slalom. Well, more generally, it could be something like this, I don't know. Oh yeah, this is okay. And you have your slalom phi. And well, and the condition to, well, the order, the different real. So the point is that the extension of S, if you extend to some S prime, you cannot get inside what is covered by the slalom. Okay, this is a way to, a natural way to add an eventually different real. Now that we have this classification, so this actually has like two natural components. The first one is the finite sequence, and the second one is this size. Okay, so we could think about the eventually different forcing as the union of sets indexed by S and M. Okay, this will just be the set of conditions such that the first coordinate is S, and such that the slalom is bounded by this natural number M. So you can write E as a countable union of these sets, and we can prove that these sets are actually Frechet linked. Okay, and well, to prove this, it is used like some, well, if you take a countable sequence there, as they have like the same S and the same M, so you have countably many slaloms, you take like some ultrafilter limits, and the condition that results taking this ultrafilter limit will force that, yeah, infinitely many things of the sequence are in the generic. So this is more or less like Miller's proof, actually. So it's just a way to formalize the notion, okay? So E is sigma Frechet-linked, and actually any complete Boolean algebra with a strictly positive additive measure is also sigma Frechet-linked. In particular, any random algebra is sigma Frechet-linked. Okay, it's not hard to see that if you look at the objects of measure bigger than or equal than 1 over n, this is a Frechet-linked set. You see, it's not hard to prove. Okay, so mostly like this notion is like really present on forcings and even on iterations when you want to preserve or you want to preserve unbounded families, or saying not adding dominating reals. So actually this is the second part of Miller's result, that you don't add dominating reals with E, and actually it generalizes that actually no sigma Frechet-linked poset adds dominating. So just this notion is enough for not adding dominating reals. And well, and actually coming back to the previous theorem of preserving math families, this is somewhat a good set for preserving math families. So this is somewhat a similar result on the previous that I talked, that was with Fisher, Friedman, and Diana Montoya. But this was in a recent paper that will be published either this year or next year, that I could generalize this a little bit more. So it is the same thing of preserving a math family by the Hechler poset, but in the first item is not just E random or co-enforcing, but actually you can have some nicely definable sigma Frechet-linked poset in your iteration. And besides, you are not restricted that the size of the math family you add is regular. You just need to have a lower bound, a regular lower bound for the size that just control the small posets on the iteration. So this is like somewhat some simple generalization, but I want to look for more, okay? So let's see. So now one particular thing that I mentioned about this forcing or this union or these components is that we use there are used ultrafilter limits to prove that they are Frechet-linked. But actually the use of the filters actually tells you more about the property of these sets. And this is like somewhat a generalization of the previous notion. So we fix a forcing and we fix a filter on omega, any free filter. And for a subset of the forcing, we define what it means to be F-linked, linked with respect to the filter, which means that for any countable sequence on the set, you can find some condition forcing that the set of indexes of the things that are in the generic is positive with respect to the filter, meaning that it intersects every member of the filter. And likewise, not likewise, sorry. And you can just compile this in what is called ultrafilter linked, which means that it's F-linked for any filter. And you can talk about, similar linked and Naster notions, mu F-linked, mu ultrafilter linked, and also you can define the Naster properties. And actually, well, what I mentioned here, as you use ultrafilter limits there, you have that eventually the forcing adding eventually different real is sigma ultrafilter linked. Actually, all these components are linked for every filter, right? But there is one surprising thing, and is that in the interesting cases when you are CCC, this notion of ultrafilter linked, which is the strongest, is morally the same as Frechet linked. Okay, so this is satisfied by forcings that are PCC, where P is the pseudo intersection number. So actually, this is not difficult to prove. So I will just roughly sketch what you can do. So we have a filter F, and we have some sequence. And we assume that the sequence, or when we look at the sequence, or the indexes that are in the generic, it's in the dual ideal, meaning that there is some member of the filter such that the set of indexes of things that are in the generic intersected A is empty. So we can say this, okay? So we can then choose a maximal anti-chain. So A subset of P a maximal anti-chain, like deciding this object that comes from the ground model. So this will decide, I don't know, like AP, for a condition here we decide an AP that has empty intersection with this set. But as it's PCC, from this AP we can find a pseudo intersection of all the APs. Of course, this pseudo intersection could be outside the filter, but it doesn't matter. It's just an infinite. The important thing is that this is an infinite set. And now, when you look at at your sequence, but restricted to this infinite set, it is forced that only finitely many of these things are in the generic, and therefore you cannot be Frechet-linked. So yeah, it's a simple argument, a very nice one. So then, what's the need of talking about ultra-filter linked if just the filter-linkness is enough? Well, the thing is iterations. So, well, or iterations or products, okay? So when we look at products, we need ultra-filters to preserve the products, okay? So the product of two delinked sets are delinked when D is an ultra-filter. And as a consequence of this, the finite support product of kappa D-Naster sets posets are also kappa D-Naster. And we have something similar with finite support iterations. The finite support iterations of Frechet-Naster stuff is again Frechet-Naster, and the same holds for ultra-filter-Naster. So just this relation is what helps to keep everything. Okay, I know I'm a slow speaker. I have to speed up a little bit. So now, well, one notion here is strongly unbounded families. So we say that F is a kappa strongly unbounded family if it has size larger than kappa, well, bigger or equal than kappa, and each bounded set has size less than kappa. So it's quite a strong unbounded family. So for example, co-enforcing at such stuff, okay? One natural thing that is present in many proofs using like delta system arguments in finite support iterations, but actually like works like very general even if you don't have an iteration, is that any kappa Frechet-Naster poset will preserve the strongly unbounded families from the ground model. Okay, so this is like a natural argument that appears in many places. I'm not sure where it comes from actually. But now we look at strong math families. So as I'm short of time, I'm very sorry I cannot go through details here because they are quite technical. But dually, using notions of Rendell and Fisher, we can define what is a kappa strong math family, which is like analogous to having a strongly unbounded family, that you have that the family is big and that some bounded set in some weird relation is bounded. Such a thing is always math. I wanted to say why it was math, but I'm sorry. In particular, the family added by the Hechler poset adds Hechler posets adds this type of math families. And now the main result of this talk is that the kappa Frechet-Naster posets, they preserve the kappa strong math families. So this is like quite the generalization because we are not talking about iterations anymore. And actually, well, the previous result was kappa Frechet-Naster because it has an iteration of nicely closed things. I wanted to go to the proof. I apologize again, or 1,000 times for not giving the details here. So now the applications. First, I want to quote one result joined with Martin Gorscher and Saharon Shelah, where we divide the left side of Chihon's diagram. So the challenge here is that, okay, we have a finite support iteration, but to increase this cardinal, but not that much, you need to restrict the forcing E. And then when you restrict, you may be in danger of adding dominating reals. So they have like to be controlled using ultrafilter limits. Okay? So along with the iteration, at the same time we have to construct a sequence of ultrafilters like simultaneously in order to have this control. But now with Brendle and with Miguel, we could extend like this, just separating the covering of Miguel additionally. And the funny thing is that this proof is simpler, because here, well, you could do it by a matrix iteration. So you construct first the matrix iteration. So as your matrix is already constructed, when now you want to preserve some unbounded family, you only need to look at one countable delta system. These are just technicalities.
What is the difference between dotted arrows and black arrows?
Sorry?
We have some dotted arrows and some black arrows.
The dotted is that this is the minimum of B and Kof Miguel, and well, dually that this is the maximum of non-Miguel and D. Yeah, I should have said that at some point. Yeah, it only means that. So we have like this additional cut, okay, and well, some other like nice model. Well, I have to say that, well, Yakov, Martin, and Saharon, they proved that we can divide Chihon's diagram in 10 pieces, like in the maximal possible pieces, using strongly compact cardinals, okay? But this is, well, not using compact cardinals, only CFC, and well, this is, I think, an independent result from that. So now I get to my final slide, well, just citing the result I was just talking about. So it's necessary for strongly compact cardinals to separate all the whole diagram left, and then you use the compact cardinals to separate the others. But in the model that we constructed with Georg and Miguel, we already took care of one additional separation. So using the same Boolean ultrapower things, actually 3 strongly compact cardinals to separate everything. Okay, so it's just like only one step ahead of getting rid of the compact cardinals. Sorry?
1 out of 4.
Of course, yes. Yeah, it's just like one step. Of course, what follows may be much harder, I think. So yeah, I guess I got to the end. Thank you very much.